So with all of these, we're just dealing with the series that represents some functions. A lot of the ones that we did yesterday, I think all of them, and then this one here, you're not actually given what those functions are. So it's pretty common. So you're not necessarily hammering out a bunch of derivatives like we did in the notes. So in this case, similar, we give you, or they're giving you a bunch of functional values and derivative values, but we don't really know what that function is. So in part A, you wrote a third degree Taylor polynomial for f. That hopefully was pretty nice. Letter B, they're introducing a new function that we again don't know, and this is going to be g. And what g of x is going to be equivalent to is the function from A that we don't know, but instead of a function of x that we would have done in part A, we're going to take whatever this unknown function in A was, and we're going to write it now with a composite of x squared. And we want it to be a fourth degree Taylor polynomial. So in terms of the setup here, g of x is going to equal f of x squared. So that's what they gave us in the setup of this problem. Right, it's really messed up here. And then we want to come up with a fourth degree Taylor polynomial for g of x. There we go. So let me move this up. So we're going to call this p sub 4 of x, or fourth degree Taylor polynomial. And remember, the fourth degree doesn't mean we're going to have 4 terms. It means we're going to go to our fourth power, because this one will not have 4 terms. If we go back up to part A, this is f. This is an approximation. So let me write this as an approximation for f. That's what we did in part A. So if that is f, and we now want to write this as a composite of x squared, all that really means is if this is f of x, then everywhere I have an x, we're going to replace that x with a new composite of x squared. So if this was our first term, that one's not going to get changed at all because we don't have an x to change the composite with. However, the next one, instead of a 3x, if our new composite is x squared, you would have minus 3, and then again, instead of x, you're plugging in an x squared. When we go to the third term in part A, you would have had x squared over 2 for the function f, but instead of x squared over 2, we are changing our composite to be x squared. That is largely your answer. Isn't that giving us now a power of 4? And that's what the question was asking for, a fourth degree Taylor polynomial. You can simplify it if you want. This one isn't terrible to simplify, but again, there's no need to simplify this to get all of the points. You can just write it as what we had in that previous step. But if we write it like this, a little easier, hopefully, to understand, that's our fourth degree Taylor polynomial. You're done. All right. So again, it's the whole idea of a series or a polynomial used to approximate a function. So old stuff, composites, products, integrals, derivatives, we just do them with the polynomial if the polynomial represents the function. Okay? All right, letter C. You're going to write a third degree Taylor polynomial for h. So we have another new function. And what they're telling you to do to figure out what h is take the function that we did in part A, and we now want to find the antiderivative of that function over the interval of 0 to x. All right, so let me see if I can squeeze this out, moving this down. Right, I might regret not dropping this down, but let's see if we can squeeze it in the right-hand side. So h of x should equal the definite integral of 0 to x with the function f of t dt. All right, so if we're going to do, I'm going to use an approximation symbol just so we know that this is h of x. And what we're going to be integrating over the interval of 0 to x is the function f. And f goes back to part A. All right, when we did this Taylor polynomial in part A, we were doing this to approximate the function f. So we want to integrate that now. So we're going to do the integral of 5 minus 3x instead of x. However, they're telling us to write this as a function of t. So don't write 3x, write 3t. Instead of x squared over 2, you're going to do t squared over 2. Keep in mind the end game here. We ultimately want a third degree Taylor polynomial. So the reason we're going to stop at this term right here is because if we're ultimately doing the antiderivative, which is what this integral tells us you're going to be doing, if I do the antiderivative of a t squared term, wouldn't that then in the next step give you a t cubed? Right, so that's why we're stopping at that term. So the function h of x is approximately, we just go through this antiderivative. So the nice thing about this chapter is a lot of review of old ideas here. So if we now go through, find your antiderivative, we're going to evaluate that from 0 to 6. Whole upper limit, subtract lower limit, and what we get is h of x would be approximately 5x minus 3x squared over 2 plus x cubed over 6. That's your upper limit plugged in. You do plug in your lower limit, but every single one of these terms has a t in it, and you're plugging in a 0, so that would all drop out. That's your answer. Make sure you're using approximations here, unless at some point in time we write it, and typically I kind of like writing it as the polynomial because people, even I do it, so used to writing equal signs. But you can only use an equal sign if we're saying that that's the third degree polynomial. Anything else, make sure you have that approximation. All right. So there's 3 of these. I think we've seen 4 now total of these endless supply of these questions from every year. All right, what's our next one? Part A. Part A should be easy at this point. So knock out part A. Hopefully this is kind of like this a week from today, that you just get a simple little one like this. Part A is just writing a third degree Taylor polynomial. So do that. Part A should be nice. And then go ahead and approximate f of 1.5 using that polynomial. Okay. I can give you the functional value. Just make sure you have the polynomial. You don't need to spend time plugging all that in. Everything you needed was given to you in the setup of the problem. So really nice, direct, simple little question. You're given your functional value. That's how these will start out. So you get your -3. So that's like your 0 derivative term, your 0 power, 0 factorial. Then your first derivative, your second and third derivative are all given. We're centered at 2, so these should all be x minus 2's. And then first power, first factorial, second power, second factorial, on down the line until we get to the third polynomial, or the third degree term. All right, we all got that right, hopefully. All right, then you're going to plug in a 1.5. You must use this approximation symbol, and that should have given you a -4.958. All right, and that's ultimately the answer to the question. So we do want to go back to f of 1.5, and then just make sure we use that approximation symbol. Okay. All right. Then letter B, a little weird now, but it's another error idea. So a bunch of the questions, and the last one we didn't, but the 2 we did yesterday in their entirety had some error questions. So it says the fourth derivative of our function would satisfy this inequality, right? So this is just saying that the fourth derivative, absolute largest value possible, would be a 3 on this interval of a -1.5 to 2. So it says, using our error bound, on the approximation that we just found in part A for 1.5, explain why it would be impossible for the real value of 1. Holy. Put your helmets on. All right. Careful over there on that side of the room. I feel like he's over there, ready to fall through the roof. I think they're doing the solar panels up there, but that was pretty loud. Just get under your desk if you need to. It's like the old, when you're in junior high and they get you under the desk for the tornado drills. Okay. So now we want to show, even though we don't know what f of 1.5 is, we want to show that there's no way that it could equal a negative 0.5. So a lot to put together here. This one is a little trickier in terms of the wording and understanding what this is asking. But again, pick out key ideas, understand sort of what this is really testing you on. Certainly this is one of our little error ideas. And we know the error has to be less than or equal to that first unused term, because with every term we add, it gets unused term. Every term we add gets more and more accurate. So the approximation we use was a third degree Taylor polynomial to get this guy. So wouldn't the first unused term be our fourth degree Taylor polynomial? So whatever this term would have been right here that we didn't do, that would have produced the largest error possible. That's what we want to put in here. What would that have looked like? So for sure, you're going to have an x minus 2 to the fourth power over a 4 factorial. And then what we would have needed right here is our fourth derivative value at 2. That would have been the next term. If you look at the setup of the problem, they don't give you the fourth derivative. They stopped us right here with the third derivative. They don't give us the fourth. But isn't that what this is now alluding to? That the fourth derivative would have satisfied this inequality, that the largest possible value this would have been is a 3. So if we want to show that there's no way we could equal this, what this is really asking to do is find the largest possible error that would have been available to find for that approximation. Well, isn't the largest value that we could have gotten out of this guy right here, isn't the largest value we're going to get is if the derivative was a 3. If you use a 1, even though it satisfies the inequality, that's going to be a smaller error than if we use the 3. So we want to use that 3, and we want to evaluate it at the x value that we were given, right? The 1.5. So now we want to know when x is a 1.5, what does that equal? So that's our fourth term. If we would have plugged in the 1.5, that thing would have had a value of, and I can give you this, at this point it's just calculator issue, 0.008. So our error has to be less than or equal to the absolute value of 0.008. Now, we still have a little work to do, but if nothing else, that would have accumulated some points for you. If you understand it's an error question, that it's the first unused term, we could set that up. We would hopefully all be able to kind of get to this. That third and final point is where you have to really kind of understand what this question is getting at. If we want to show that f of 1.5 could never equal a negative 0.5, isn't this our approximation? So I'm going to take that value, the negative 4.958, and couldn't our error be 0.008? Notice how it's an absolute value. Couldn't it be 0.008 bigger or smaller than this value? That's the largest possible error that this could have been. So this value could have been increased by a possible error of 0.008. At the same time, it could have been decreased by a possible error of 0.008. It's got to fall within this little window. If you then evaluate those, and I can kind of give you this should give you a negative 4.996. The big end would give you a negative 4.950. Okay, so write that down, make sure we understood this. So this was our approximation. If I included the possible error, the largest possible error I could have gotten into, then my functional value at 1.5, while we don't know exactly what it was, had to have fallen within this window. Notice how in this step right here, when we write it like this, are we now showing that f of 1.5 could never have equaled the value of a -5? Does -5 fit in this window of values here? No. So that you would want to kind of pull it together at the end with some sort of a statement like this to actually then answer the question the way that they were asking it. Okay. Again, on this day, if you could have put that together, that's great. But there's really no reason we start seeing error that we couldn't have at least gotten this part of it done. And then maybe we don't necessarily kind of figure that last step out, but you're still accumulating points along the way. Okay. Somebody have their hand up. Yeah. Who we got there? Darda.
Shouldn't it be negative 4.966?
I don't know. Is it? I put 4.996. Is it 66? Yeah, that would make sense. Yeah, for sure. Without even looking at the calculator. Yeah, this should be 66. Thank you. Can't read my own handwriting. Yeah. Let's change that. Back there and here too. Yeah. Nice catch. All right, we go to that. All right, part C then, last one of these guys. So it says, write the 4th degree Taylor polynomial for g of x, and g of x, you are told, is the function that we use in part A, but now we're changing our composite to x squared plus 2. So that's why the more you see, hopefully the easier it gets. We've done a very, very similar problem a minute ago, where we already knew what f was, and all we really wanted to do is change the composite. So if we go to what we found in part A, and I'm going to again use f of x, but then we're going to use an approximation, just so we understand what we found f of x to be in part A. So part A, if you look at your answer to part A, we had this, the -3 plus the 5x minus 2, all this good stuff. So this is f of x, at least as an approximation. So all we are now really doing, are we in this statement right here, just saying take that function f and now write it as a composite with x squared plus 2. So if I want to find g of x, I'm going to use an approximation here, take this function, and now wherever you have an x, we're changing that composite here, anywhere we have an x, your new composite is going to be an x squared plus a2. So the -3 isn't going to change. But for the next one, instead of x minus 2 to the first power over a 1 factorial, let me move this up here. In the position where we had an x, our new composite is this x squared plus 2. So we're going to put in an x squared plus 2 right here. Then we go to the next term. We would have had 3, and then I would have had an x right here, minus a 2 squared over a 2 factorial. But where this x was, we are now in that position plugging in our new composite of x squared plus 2. Following this? We wanted a 4th degree Taylor polynomial. If I move my screen up, or if you look at part C on your paper, you'll see the very first 4 words, find the 4th degree Taylor polynomial. Won't this now give us a 4th degree when I square that square? So we don't really need that next term. If we clean this up, you can keep writing g of x if you want. I'm going to put this as p sub 4 of x, just so we can understand. That's a 4th degree Taylor polynomial. Notice how we're also supposed to be centered at 0, right? It has to be centered at 0. And these are going to cancel, so we just get 5x squared. Here the 2's are going to cancel as well, so we get 3x to the 4th over 2 factorial. And then that's our 4th degree Taylor polynomial. So just a composite function, right? Don't overthink it. Just understand that's what that's asking. Good with that part? All right, now the second part. So this says use p, so that's what we just found right here. Here's our 4th degree polynomial. To explain why g, there's a lot of variables getting thrown around, but what p sub 4 is the approximation for g. So that's the polynomial that's approximating the function g. Move this up here. All right, then the question is, explain why G must have a relative minimum at x equals 0. So here's what this gets to, something we talked very briefly, maybe 15 minutes on, that sometimes gets popped up with these polynomials. So we want to show that we have a min at x equals 0. All right. So the way we're going to do this is, let's say I took g primed of 0. The negative 3 is going to go away. I'm going to get a 10x, and then I'm going to get a 12x cubed over 2 factorial. If you want to simplify it, feel free. It's not necessary. Now, understand, this is an approximation for g. So we don't want to factor this, because in reality, g, and I should have an approximation symbol there, sorry. So we don't want to factor that, try to set that equal to 0 and do our sign chart, because this really does have a whole bunch of infinite terms behind it. But what we can do, so in the next step, at 0, don't we have a value of 0 there? The derivative has to equal 0 at that point. It must. Because every term after this, it looks like we're going to have an x to the 5th, and then an x to the 7th, and then an x to the 9th. If they all have x's in them, when I plug in a 0, don't they all zero out? So what this gets at, it's what's called, and we talked about it briefly, you may or may not remember it, the second derivative test. Whenever we had this, so whenever our derivative equaled 0, there's only 3 possible things that could happen. You either have a max, that gives us a slope of 0. You could have a min, that gives you a slope of 0, or we can have a point of inflection, like the cubed graph flattens out momentarily. So as soon as you see this right here, then that tells us that one of these 3 things has to be happening at this x value of 0. It must. Well, let's now go to the second derivative. Notice how the second derivative would be a 10. And then we would get 36x squared over 2 factorial. And we would still have all of these extra terms behind it, like an x to the 4th, x to the 6th, x to the 8th, so on and so forth. So the reason it's called a second derivative test for maxes and mins is if I now type in or plug in a 0 into this, wouldn't this term and all subsequent terms all go away? And the only thing you're going to be left with is this 10. Most importantly, it is a positive 10, telling us that our function must be what in terms of concavity if the second derivative is positive? We are what? Concave what? What? Up, right? So of these 3, this one is concave down. This one is changing concavity at this point, all right, from down to up. The one that is concave up at that same place where the slope is 0 is this guy right here. Is there a minimum there? Yeah, so that's the second derivative test for concavity, and that's what they're asking you to look at. Explain why there must be a minimum at x equals 0. Explain, unfortunately, and they don't do this too often, this means you have to use words. So we can't just leave this out there and let them kind of decipher it for themselves. Explain means we have to put this into words. So we would just say, there is a min because g prime equals 0. Therefore, g has a max, a min, let me not use slash, comma, max, a min, or a point of inflection. And then since g double prime equals 0, g of x is concave up. Oh, yeah, good call. Yeah. It's positive, that's how we know we're concave up. You will see that is It's hardly ever used. This is really the only time I've really ever seen a question, a few times with these types, when it's a polynomial in a series. Because normally we just do our sign chart, look for a positive to negative sign change, all that good stuff. And it doesn't work that way when we're dealing with these series. So that's where you're going to want to kind of know that second derivative test. Okay. All right. Is there one more? All right. Mercifully. Last one. All right. Part A. Normally part A's are really nice. This part A has a really nice one and a really tricky one. Actually, I think these are both somewhat hard. See if you can get part A. It gets easier after this. But I think one of these is really hard. You need to be real clever for one of them. Are we at least getting f prime to 0, maybe? Even that I think is not necessarily, depending on how you do it, not quite as nice as some of the ones we've done in the past. All right, let's talk about f prime to 0 and see if you got that. And then if you think you're on the right path for the 17th derivative value at 0, then let me know. All right. So f prime to 0, there's really a couple of different ways that we could approach this. Isn't f of x equal to this? And we can use an equal sign because you're given this statement right here. So these are 100% equivalent to each other. We can use this. So there is nothing stopping us in terms of finding f prime to 0, treating this like a regular old function that we would have dealt with the first few weeks of the year, where I could just take this derivative, the 1's going to go away. The derivative of x would be a 1, so I get 1 over 2 factorial. The derivative of this guy would have been 2x to the 1 over a 3 factorial. We don't need to go a whole lot farther than that because won't every term after this have an x in it? So can I now, if that is my derivative, can't I just plug in 0? And the only thing I'm going to be left with, since all of these terms back here have an x, won't I just have 1 over 2 factorial, which is 1/2. Right? So that's one way that we can approach in terms of getting math. So if you got 1/2, that is correct. That is not a real practical way, even though if you notice the pattern, it'll get you there. We don't want to hammer out 17 derivatives though, right, for the second one and throw in a 0 to that. That'll keep it busy for a really, really long time. You have to write out like 18 terms of these, and then you would need to continue on forever and ever and ever. Okay, but if you understand what's happening when you do that, it's a way to kind of go about it. So let's go to this up here real quick. If this is a Maclaurin series, and this is a power of 1, if that's a power of 1, then didn't that, if we did our little Maclaurin series, f primed of 0, I should then have x to the first power over a 1 factorial. Shouldn't that be this first term? So if you look at this coefficient, doesn't 1 over 2 factorial have to be equivalent to the derivative value divided by 1 factorial? So I'm going to set that up. So f primed of 0 divided by the 1 factorial in this particular problem became this 1 over 2 factorial. I'm good with that. So I'm going to erase it. All right, and the next one. No, I won't erase it. Not all of it anyway. Erase this. If I wanted the second derivative, second power, second factorial, that would be this term right here. So we have the x squared, but notice how we got 1 over 3 factorial. So 1 over 3 factorial has to be equivalent to f double primed divided by 2 factorial. So I am now going to say that the second derivative over 2 factorial equaled 1 over 3 factorial. And then now we'll see if we kind of see this little pattern here. So come down here, let's solve this for f primed of 0. Wouldn't I multiply the 1 factorial over, and I would get 1 factorial over 2 factorial. That's a really, really fancy way of saying 1/2, right? Same thing that we just got right here for our answer. If I want the second derivative value at 0, can't I multiply the 2 factorial over and say that the second derivative is 2 factorial divided by 3 factorial? All right, are we all seeing how this is playing out? So that if I now want the 17th derivative, that's a 7, at 0, that would have to be what over what? So if f primed of 0 is 1 factorial over 2 factorial, the second derivative is 2 factorial over 3 factorial, this would have to be what, Ashley? Good. 17 factorial over 18 factorial. You could leave that. It's a perfectly acceptable answer. Isn't that really, though, 1/18? Because all the 17 through 1s would cancel. You're just left with that 18 in the denominator. That would be your 17th derivative value at 0. That to me is sneaky. Now, think about hammering out 18 derivatives, though. Wouldn't you just be doing 2 times 1 and then 3 times 2, 4 times 3? Aren't you basically playing out the factorials that whole time? So you can kind of think of the pattern as well. That eventually kind of would have revealed itself to you. But certainly don't try to take too many derivatives without seeing some sort of a pattern. Okay? That's pretty tricky. That's usually harder than what the A's normally are. But then they give you a really nice one for B. All right, so B, we should get all of these points. So go through B. They give you the general term, so nothing sneaky about that. Here's your general term, and it is just a straight up interval of convergence. All right, so do the interval of convergence for this series here. It's not even that hard of a series, okay? And then we'll see if we get the same thing. Okay, keep going. This is not letting me erase. I think you can do this one. Interval of convergence is one of the things we've done the most of together. So we hope we could do that. Right. So you do your n plus 1 series, so that's x to the n plus 1 divided by the n plus 2, because n plus 1, and then multiply by the reciprocal. Then this for sure is going to cancel. This x to the n is going to cancel out that x to the n. And then it's just a matter of making sure we don't do too much work here. If this is an n plus 2 factorial, notice how you have an n plus 1 factorial up here. So when I rewrite the x that's left, I'm just going to take this n plus 2, and I'm just going to continue until I get to an n plus a 1 and then stop, and then identify that this does go on with a little factorial behind it. Because I have an n plus 1 factorial in the other numerator, that these would then cancel out. All right, did we do that correctly? All right, then all you're left with is an x over an n plus a 2. We've now seen this a handful of times here in the last few days. As n goes to infinity, this is one of the ones where notice how there is no n in the numerator. So isn't it just your denominator that's getting larger and larger and larger and larger and larger? So this should have had a limit of what? Okay, zeros. Yeah, see zeros on people's fingers. That is always less than 1. And then in regards to the actual answer to the question, the interval of convergence, it doesn't matter what x is. Any x value is going to give you this limit of 0. So this is one of the ones that we would say our interval of convergence is negative infinity to infinity. Whatever this function is going to produce an exact clone everywhere of that function with this polynomial. Okay. All right, last one, because we can do C. Letter C. And we'll do D tomorrow. And they're clever. So this is clever of them. It says let g of x equal x times f of x. And then write a Maclaurin series for g of x, showing the first 3 terms. I guess D is the one they're clever on. So g of x is simply x multiplied by f of x. Remember, f of x, they gave to us. So aren't they really just saying if I want g of x, you're just going to take f of x, and you're going to multiply it by x. So if I'm going to multiply this by x on the left-hand side, doesn't that mean I can just come over here, since these are equivalent, and multiply that guy by x? Do that, showing the first 3 non-zero terms. So isn't that really just going to be x times 1, x times this, and then x times this? And then once you've done that, because that's not hard, write the general term for that. See if we can come up with the general term that would then produce g of x. Let me erase all this. All right. When we write the general term, we don't have a ton of time here. When we go to write this general term, what do we think for this exponent? Here's the thing I was going to say first. Where this one starts is where the new one needs to start as well. So what I mean by that is, because with a lot of these, you can kind of start anywhere you want. But wouldn't this one have to start at an n value of 0 in order for us to get 1 for the first term? So the new one that you're going to create, make sure that if I use 0 as the first n value, it's going to give us these terms and not the n value of a 1. Okay, so if I'm going to start with an x and n is a 0, this exponent had to have been x to the what? N plus 1. Because if I plug in a 0, I'm going to get this x to the first. And then we have a denominator. This is 1 factorial, 2 factorial, 3 factorial. In my denominator, how would we get a 1 factorial if I'm starting at a 0? Let me think. Yeah, just another n plus 1. I feel like my pen is on its last leg. Just in time. N plus 1 factorial. All right, that's your general term. Okay. And the bell would ring. Now that I look at the clock, sorry. There are no bells. So go. Yeah, and then tomorrow we'll do the test review. We'll finish letter D. I do want you to see that. And then we're pretty much done with Calc 2 forever. All right. All right. If you're home, yeah, the bell were to ring. There are no bells today. So you guys are free to go. All right. We'll see you guys. Thank you. You too.